Welcome back to another Bgcse past paper review. Today we're doing physics examination and we're looking at a paper 1, and this was from the year 2019. Again, remember, always write your school number. Don't forget to write your candidate number, very important. Also your surname and your initials. Again, read through the instructions carefully before you start the examination. Again, do not open the booklet until you are told to do so. Now let's dive into the first question. This one said that the diagram shows a spring balance. All right, now we have a rectangular block on the spring balance. And then it said, what is the reading on the spring balance? All you need to do is to look at the markings, and you will realize that coming from the 0 mark, which is from the top, okay, and you count the number of markings. So 1, 2, 3, 4, 5 markings in between. So you definitely know that each marking will be by 2. So starting from here, this is 30. The next line after 30 must be 32. So our reading there must be 32 newtons. All right, so let's get that in. 32 newtons. And this is D. For question number 2, it said which pair of quantities have the same unit? And so acceleration, velocity, absolutely not. Energy and work, they're both measured in joules. Okay, so definitely B is the correct answer right there. Energy and joules. Work and energy measured in joules. All right. Question number 3, it said the diagram shows a pulley system used on a construction site. And so right here it said, now what is the effort? What is the effort by the construction worker, assuming the pulley is weightless and there is 0 friction? So this is the effort right here. We want to figure out what this is. And so we have a load right here. And so first and foremost, I will tell you this, very importantly. There are 2 ways to talk about this. The easy way that you should remember, whenever a pulley looking like this going upwards, then you know that the effort, right, is equal half the load, okay? So that's an equation you need to know for this type of pulley system. That effort, let me put it right here. Effort, which is E, equals to half of the load, okay? Just to make a known of that. That's the easy way out, okay? I'm going to show you an opposing pulley system, which is which it turns downwards, and it will be a different calculation, and that is a fixed pulley. It's a movable one. Also, the next way you could think about this system is that you could think about the string that hold the pulley up and the one that going down, which is the load. And the load here is 100 newtons. So if there's 100 newton here, all right, just to think about it in this sense. You can also think about the string, which is this side of the string right here, which is this side. It's going upwards because it's holding the pulley upwards. This is where the effort is on this side. Okay, we call this E. And so what I wanted to understand is that there's a tension on this side of the string. And so the total downward force, which is 100, must equal to the total upward force. So since the pulley is in the exact middle, then both of them will be 50 each, right? 50 newtons each. So that's another way to think about it. Okay. Again, you can use a formula that the effort in this type of pulley is equal to half of the load. Okay. And so another way to look at this, well, the opposing way, if the pulley is set like this, let's say the pulley is fixed. Okay, I'm going to give a different scenario just in case you may see this. Let's say this is a fixed pulley, right? Like that. And then there is a load. Let's draw a load right here. And let's say the load is 100, right? I want to show you a difference here. All right, let's say the load is 100 newton. Then what is pulling this down like this with the effort must also equal to 100 newtons, right? So in this case, they're the same. So just in case you see this type of pulley system in an examination, you know how to treat it. Again, as I explained on this side, that, and a matter of fact, this is 2 ways. That one, the total downward must equal to total upward. So this is tension in the string on this side and the effort. So they are both 50. Or you can use a formula that effort is equal to half of the load. Okay. And so therefore, because of a pulley system, then it will be 50 newtons. So B will be our correct answer for that one. All right, let's jump to the next question, which is question number, let me see, what question is this? Question number 4. Okay, it said when only the pitch of a musical note is increased, which property of the sound wave has decreased? Okay, so now remember, you only increase the pitch. And so pitch, what causes pitch to go up is increase in frequency. And if you increase frequency, you will also have, if you increase frequency, that causes an increase in pitch. If you increase frequency, therefore mean the increased speed. And also amplitude will also, again, be increased. So therefore, the one that will be decreased right here will be the what? Wavelength, okay? The wavelength will decrease. Again, because if you think about it like this, a wave moving faster, we give you the wave cycle very, very close to each other. Okay, let me just delete that. All right, and put it this way. All right, so give it a little bit. All right, good. But if a wave is moving slower, then the wavelength going to be longer. Okay, just to point that out real quick. All right, number 5. Let's jump to number 5. And question number 5 state an astronaut brought a rock from the moon back to Earth. The gravitational field strength on the Earth is 10 newtons per kg, and the gravitational field strength on the moon is 1.6 newton. Which property of the rock would have changed? So which property will change is simply the weight. The weight will change. The mass will remain the same, the density will remain the same, and the volume will remain the same. So therefore, the only thing will change is the mass, because mass is affected by what? Gravity. All right, so let's jump to question number 6. And for question number 6, it states that the diagram shows a meter ruler, which was originally balanced at 50 centimeters mark. Identical weights were then placed on either side of the pivot. In which diagram will the ruler balance? All right, and so first and foremost, looking at the ruler, if the pivot or fulcrum is in the middle, then therefore means the weight must also be at exact the same distance for it to be balanced. In this case, which you're going to say the anti-clockwise moment is going to be greater because the distance is greater. This is less on this side. So this one is not correct. Okay. So for this one here, B, I'm looking at B. This is at 10 and this is at 100. That means the markings here is 10, 20, 30, 40. This is at 40. This is a whole 50. So therefore, in this case, you're going to turn this way towards the clockwise direction or the clockwise moment. For the next diagram here, diagram C, this is at 0 mark, and from 0 to 50 is 50, and from 50 to 100 is 50. So they are equal distances apart. So therefore, this will be our correct answer. Okay. For the next diagram at the bottom right here, again, it will move in this direction simply because the weight is further away from the fulcrum. All right, so it turned that direction. All right, so let's go to the next question now. And this is question number 7. And it said, which distant time graph shows an object moving at constant speed? And so to move at constant speed for distance time graph, one thing you need to remember is that the distance and time must be proportional, okay? So therefore, if there's an increased time, there must be an increased distance. Looking at graph A is a straight line. That means no change in distance. That cannot give you a constant speed. In fact, the object is not moving if the distance is the same over time, right? So up diagram graph B, which is this one, there's an increase, and I want to show you something real quick. So let's say put a line right here and come here, for example. If you call this 2 and call this, say 1, then the speed is 2 over 1. So that is be 1 meters per second. If you come here, for example, come here, then it will change to say about 4, which is about twice the distance I move, and twice the distance here as well. So it'll be 4 over 2, which again will give you 2 meters per second. So yes, graph B is correct. Graph C and D, they are changing in shape, so you know that there's a difference in terms of distance and time, so that those could not be correct, okay? Question number 8. Now for question number 8, right, the question reads that the volume of a fixed mass of gas is decreased at constant temperature. What happens to the molecules of the gas? And so first to point out right here, let's point this out real quick, right? If the temperature is constant, then there can't be any gain in kinetic energy, because as I mentioned in the previous paper, that in a previous paper, matter of fact, that kinetic energy and temperature, they are proportional. So if the temperature is constant, then the kinetic energy will also remain the what? Will all remain the same. It will be constant, okay? If you increase temperature, then you increase in kinetic energy. That's something you need to know, okay? If you decrease in temperature, there's a decrease in kinetic energy. So they are proportional. Now, momentum, their momentum increases. Again, if the kinetic energy is the same, which means the speed is the same, that means momentum must be the same, right? So those will be constant. Option C says they hit the side of a container more often. Yes, because they'll be closer to each other. All right. So definitely yes. And for D, moving slower, no, because again, temperature is the same, which means the kinetic energy will be the same. They will move at the same speed. Okay, so the answer there is C for question number 8. Now for question number 9, it said person B watches person A fires, person A fires a starter pistol. Person B hears the sound 2.5 seconds later. Calculate the distance D between person A and person B. Now, first and foremost, let's think about this. We have our time, which is 2.5 seconds. And we have our speed right here, which is 340 meters per second. So how we're going to calculate now distance? It is the velocity times time. Because remember that velocity is equal to distance over time. So for us to find distance, it is velocity times time. So therefore, we're going to multiply here our 340, so 340, okay, multiplied by our time. And let's go back to time a little bit. It is 200 and what? 2.5. So multiply by 2.5. And so here we'll get 850. Yes, it's 850. All right, and that's meters per, that's meters. Matter of fact, okay, and so 850 is our answer, and so yes, D will be our correct option. Now just jump to question number 10. For question number 10, it said which of the following is true about the image formed in a plane mirror? And the image formed in a plane mirror must be the same distance behind the mirror. That's one thing you need to know, okay? They're also the same size as well. All right, so it's an inverted, which is not true. Okay, so inverted is not true, and real is also not true. It's a virtual image, and I think the question didn't mention it. Okay, great. But the image is not real, it's a virtual image. Smaller than the object, no, they are the same size. And D is the same distance behind the mirror, and object is as object in front of mirror, so this one is correct. All right, so the image is the same distance behind the mirror as the object in front of the mirror. All right, so great. Now, question number 11, it said, which of the following diagram is a second-class lever? Now, let me quickly remind you about this easy method how to figure it out, and this is Flea. So, Flea, again, is, let me just do it real quick, F, okay? So, F, L, E, okay? F, L, E. Let me just erase this. Okay, let me take this back off. All right, this one, you really do this better. Okay. All right, great. So again, FLE, you need to remember in terms of the class of lever. And so F represents the fulcrum, L represents the load, and E represents the effort. So what I'm saying here now, if it's a first class lever, then the fulcrum must be in the middle. If it is a second class lever, the load must be in the middle. And if it's a third class lever, the effort must be in the middle. So Flea tells you what should be in the middle of the lever to classify that lever, right? Okay, so Flea, just remember it in that order. F, fulcrum in the middle, first class. Load in the middle, second class. Effort in the middle, third class. So now let's go back up here now and classify these levers. And we're looking for a second class lever. All right. I know some of you will know it by looking at the image because you remember it. So the effort is here, okay? Effort is here in this, in option A. The fulcrum or pivot is in the middle. So this is a first class lever and the load is right there. That's a first class lever. For the wheelbarrow, the load is in the middle, okay? The fulcrum or the effort will, or the pivot, sorry, will be here. So the fulcrum or pivot will be here. The effort will be on the handle, lifting the wheelbarrow. So therefore, this is in the middle. The load is in the middle, and that is our second class lever. So option B will be our correct answer. Let's identify D. Here is the fulcrum, okay? The effort is in the middle. This we're going to press on, okay? So the effort is in the middle and the load is at the end. So this is a third class lever, all right, and that is a staple remover. A person using a wedge, for example, or they're using a lever to roll a stone. So it could be like a crowbar or just a piece of board. And so again, this here will be the fulcrum in the middle. The load will be this, and the effort that the person is placing on that piece of plank. All right. So this will be a first class lever. Okay. So now classify all of them, and definitely B is the correct answer. Now let's jump to question number 11. All right. And so for this question here, it reads that whilst flying horizontally at a constant speed, the pilot increases the lift, which is this part, increase the space, and the drag. So also increase the drag as well. All right. Increase the lift and the drag of the aircraft is by the same amount. So both of them increase by the same amount. The thrust and the weight, they remain the same. And it said in which direction could the resultant force act on the aircraft? And so again, if the drag is greater than the thrust, that means the airplane or aircraft should be going backwards, and also the lift will cause a pull on it. So it will not go exactly backwards, but it will fall somewhere in between these two forces. Okay. And how you can think about this as, again, to make it easy for you, you could think about a triangular shape, which is a vector. So you have this force going that way, this force going this way, all right? And then we can think about completing this as a, all right, let me just continue these straight lines here. All right, so let's continue this as a rectangle, and then we find our hypotenuse inside of this point right here. So this will be our resultant force in the middle here. So definitely our resultant force must look something like that, okay? All right, so let's go to the answers now and see which one is looking like R, which is the resultant force between the two forces. All right, so here now, okay, here we have it. B will be our answer. B, so now that shape appears there. Okay, awesome. All right, so let's go to question number 13. And in question number 13, it reads that the table below shows some common physical quantities and their units as well. So the question is below the table here. It said, which physical quantity in the table is correctly matched with the units used for its measurement? And so energy is not measured Newton per meter squared. This is force over area, and you know that that is pressure, right? So that is not correct. Force, kilogram meters per second squared. What do you think about that one? Because remember, yeah, this is correct, because remember, mass times acceleration is force, right? So force is equal to mass times acceleration. So you can remember that force is equal to mass times acceleration. So this unit is correct. So I could actually highlight this one. Momentum, that is not correct right there, because again, momentum is the mass times velocity, okay, which should give you kilogram meters per second, okay? Moment is simple force times distance, so that should be Newton meters, not kilogram meter. All right, so 13 is B. Now for 14, let's go to 14. It said the motor shown as a power output of 60 watt. It is used to lift 10 Newton object vertically, And so the motor direction here, which is counterclockwise, so this is counterclockwise going the opposite direction as the clock. And so here you have a 10 Newton forces there. So the question now reads, what is the greatest height this motor could raise the load in 1 second? Okay, so let's talk about what is given here. So we could talk about the power, which is 6. Let's write them down real quick. So power here, power is equal to 60. Okay, so that's 60 watt for the power. And let's talk about now the force. So the force here is equal to 10. Just write them down real quick. All right, and we also have time. They say in 1 second. So the time here is going to be 1 second. Okay, so now we have those 3 quantities: our pressure, sorry, our power, our force, and our time. Okay, so 1 second. I must write in these units in Newton, and this is watt. Okay, so those are 4 quantities. Now they ask us to find the greatest height. So I want to find height. So first and foremost, what I want to talk about here, right, is that power. Let's give you a formula for power. Okay, so power here is equal to force times distance. So which means the force times distance, or we could just say work over time. So work over time, let's break it down, and then we're going to break it down. Work over time is also equal to force times distance, right? So work over time, because work is force times distance. So force, let's say force, that's not F, force times distance, all divided by time, right? So let me just put it here, all divided by time, all right, because that's the same thing, okay? So I just want to point it out that work is force times distance divided by time. That's where we get that formula. So what can we do now, all right, is to find distance here, okay? So if P is equal to force times D over T, then we could make D be the subject of the formula. How are we going to do that? All right, let's plug our information in. We have the power, we have the force, we have the time. So here now we can simply say that so let's, matter of fact, let's just kind of apply this real quick, right? All right, so here we can say that distance, let's put distance is equal to the power, okay, the power multiplied by time times time, okay, all right, and then you're going to divide it by what? Divided by force, okay? So we're going to divide by force. All of this will divide by force, okay? So let's divide by force right here. All right, let's put a line there so you see exactly what I'm doing. All right, and so we're going to plug our information in now. So force here is, all right, so let's put our power. So power is 60. So P is 60 times time, which is only 1, okay? All divided by our force, and the force there is 10 newtons, so we're going to put 10. So again, all of this equation here, 60 times 1 is 60, 60 divided by 10 is 6 meters. So this is 6 meters. So the maximum height that this motor can lift is lift the weight is actually 6 meters high. All right, so let's now go to our option here and see if we see our 6 meters, and that's option D. All right, now let's jump to question number 15 now. And question number 15, it reads, the cooling fins of a refrigerator are painted black. Okay, so they are painted black. It said, which method of heat transfer does this improve? And since it's heated black, remember that black will absorb light easier. So it absorbs the light rays or heat rays. And so therefore, heat will move through radiation. So that is affecting the radiation. All right. Okay, great. Now, question number 16. It said, when pollen grains suspended in a liquid, so the matter of fact, let me just make a note here. The grains, they are suspended in the liquid. Okay. They are observed under a microscope. They are seen to be in continuous random motion. This is due to what? All right. So if they are in constant random motion, you're looking on them with a microscope and they're suspended to the bottom of the liquid. And so this could only because of the molecules of the water colliding with the pollens, because the molecules of the water is also in constant random motion as well. For convectional current, the particles will be seen moving through the entire liquid, because convectional current will cause the water to have like a boiling effect, going up, coming down. So you'll see the movement of the pollens throughout the liquid. Okay. All right. So question number 17 here. It said, which combination of colors may produce white light? And so to produce white light, you need the basic colors of light, or the primary colors of light, which are blue, green, and red. And so B will be our correct answer right here. Okay, so yellow is not one of the colors, so therefore yellow will be out of it. So yellow make everything else wrong. Okay. All right, so number 18 here, it said, when cooking rice, how does increased altitude and adding salt affect the boiling point of water? So first and foremost, you need to understand, when you add salt to it, right, is that the conductivity of the water now will do what? Will increase. So increase the convectional movement of the water, or the convectional flow of heat energy. And increase in altitude will decrease in pressure. So you have a decrease in pressure, so therefore means the boiling point will also decrease. Okay, so here C will be our correct answer. Question number 19. It said, what happens when water is heated from 0 degrees Celsius to 4 degrees Celsius? And so here, it said density remained the same. That's the first thing. It said, and it said, what happens to water as it heated? So first thing to think about, the ice, the ice is melting. This is ice, a matter of fact, and it's melting. So if it is melting, right, it said density remain the same. Is that true? No, because again, remember that ice will increase in volume, or water increase in volume as it freezes, and decrease in volume when it melts. So therefore, there's a decrease in volume. So density will change. It can't remain the same. Now B say density decreases. Remember, again, if you have a less volume, then the density should increase, not decrease, right? And volume again is decreasing, not increasing. And so D will be our correct answer right here, because the volume drops from solid to liquid for water. Okay, for water. That's very important to note. All right, so let's jump to the next question. Question number 20. It said, which three radiations of electromagnetic spectrum are commonly used for communication? And this one off the bat here, we know we use radio waves, okay? We use visible light, and we use microwaves. So D will be our correct answer, okay? All right. Now, question number 21. It states that a trolley of mass 2 kg is loaded with sand of mass 500 grams. The trolley moves to a constant speed of 3 meters per second. All right, so now there are some things in the consider right here, right? That if the trolley is moving with 3 meters per second, that means the entire sand and the whole thing is moving with that speed, right? First and foremost. However, now, if we want to find the momentum, so what they ask us to find here is the momentum of the trolley. So the momentum is both masses along with speed. And just to remind you that momentum is equal to, just to give a quick notification right here, that momentum is equal to mass times velocity, correct? All right, so if momentum is equal to mass times velocity, we must consider total mass right here, okay, the total mass. However, look carefully, this mass is not in kilograms, so we need to convert that mass into kilograms, okay? And then we find our total mass. So the mass here in kilograms, I'm going to convert this into kilograms. We're going to say 500 divided by 1,000, okay? And that will give us 0.5. That's 0.5 when you divide 500 by 1,000. And so the total mass over here now, the total mass, okay, so the total mass, let's just say total, and we know, okay, total mass will equal to the 0.5, which is the mass of the sand, okay? So 0.5 plus that of the trolley itself, plus 2, and that will give us 2.5. So our mass, the total mass here is 2.5 kilograms, okay? All right, great. Now you can go ahead now and multiply the mass by the velocity. So to find our momentum, it is mass times velocity, which is 2.5 okay, 2.5 multiplied by 3, okay, and 2.5 multiplied by 3 will give us 7.5, okay. And so our answer here for this question will be 7.5. Great. So B is our correct option. All right, awesome. Now let's jump to question now, number 22. It said spherical mirrors have several applications in everyday life. It said, which of the following correctly list uses of concave mirrors? Okay, so concave mirrors here, and let's go from option A. For shaving, yes, the concave mirror will make you see the image much larger, so give a larger images. And for solar cookers, what the concave mirror will do is to let all the rays will penetrate at a certain point and cause heating. All right, so distribution of heat will be great within that curved mirror itself. All right, because of the reflection of the light, and so whatever is on top of that mirror will get warm. All right, and vehicle headlamps will allow you to see the object or the image of the object much closer. Okay, so this is a good application right here. All right, so this is good. So option A is good. All right. Now the problem with rear view mirrors, all right, is that if you look into your rear view mirror and you may misjudge the distance, that could cause a serious problem, right? So yeah, you don't want it to be too far from you at all. All right. And for supermarket surveillance, you spread out the mirror. So you spread in a different angle. So that's really like a convex mirror. And so you actually see a greater amount of space, and the image will also be smaller, in fact. All right. So definitely we're going to stick with A. All right. So let's now jump into the next question here. All right. So for question number 23, it says diagram below shows the change in direction of water waves as they move from shallow to deep water. So what are some of the things that happen when they move from shallow to deep? Is that yes, you'll have some larger wavelength as shown right here. Okay, so we definitely know that. But what will also happen to speed? Will speed change? Yes. So the wave will go faster from shallow to deep water. You also need to know that, all right? So those are two basic things you need to know, that the wavelength will increase and definitely the speed will also increase. The point of source where the wave is generated from is the same. So the frequency throughout is the same. Frequency remains the same. Okay, so frequency does not change. So let's see what is happening here. So which will correctly describe what happens when waves enter deeper water. So again, when waves enter deeper water, the effect is called refraction because it's bending. So reflection cannot be a correct answer. So we know that A and B, they are out. There must be refraction. And if it's refracting, the speed remains the same. It is not true because remember the frequency remains the same, but the wavelength changes. And if it's same frequency for an increased wavelength, then the speed must increase because remember speed is equal to frequency times wavelength, right? So definitely C is not correct. So D will be your correct answer. It refracts, speed increase, same frequency, increased wavelength. So therefore it's a change in speed. Frequency here again remain the same as we mentioned. So D is your correct answer. Now question number 24, and we almost close to the half. So say the diagram shows a transverse wave moving from right to left. Okay, so moving from right to left. Okay. But this is not showing right to left. Okay, this is direction right here, position of a wave. Okay, all right, that's not really important. Okay, we can see wave motion. That's fine. All right. Now let's see what they're asking to see if the direction will actually affect anything. All right, they say what is the amplitude of the wave, amplitude and wavelength of the wave. So let's now look at the amplitude and wavelength. Okay. All right, so firstly, let's think about amplitude first. Amplitude is the height of a crest or a depth of a trough. And so if you're moving from 0 point, which is the undisturbed position, all the way up here, it gives you 0.02. Okay, so we know the amplitude is the distance from here to here. Okay, and in this case here, it is 0.02. So get the amplitude to be that. the wavelength now must be equal points between the waves. And so if you should look, for example, let's choose 2 equal points. So let's say we're moving from a trough, for example, to another trough, then you definitely know. So you're going to look at one complete cycle. So you're going to go up, okay, come down, all right, and then all the way up. So the equal points on a wave to create a complete cycle. So 2 equal points on any wave will give you the wavelength, okay? That will give you the wavelength. So let me just quickly show you the exact cycle right here. So I'm going to show you one complete cycle. All right, let me take off just this piece. I need to remove right here. So a complete cycle, which means from 2 equal points. And so the distance between 2 troughs, for example, is a wavelength. The distance between 2 crests is also a wavelength, right? Okay. So from here to here, okay, from here to here, what value will we get? All right. And so if you look at the graph carefully from point to point, let's say moving from 10 to 15. This one is easier to look at. Say moving from 10 to 15. All right, that's only 5. So from here to here, it's only 5. All right, that's the point out there. Okay. It is only 5. All right. So the wavelength must be 5. What this unit is centimeters. So it must be 5 centimeters, while the amplitude must be 0.02. Okay, so 0.02 and pretty much 5. Let's go back to make sure so pretty much 5. Matter of fact, is also less than 5. The graph is not so clear in terms of the lines, but here it will be 0.02 and 4. All right, the wave itself is not, the graph itself is not exactly on 5. All right, but just say close to 5. Yep, so that will be your correct answer right there. Okay, amplitude is 0.02. All right, and so the wavelength is 4 in this case. Now for 25, it said which of the following materials is magnetically hard? And so in other words, which of them could be magnetized? And so steel is our correct answer. Copper, iron, magnetically hard, I should say. So yeah, iron will be easily magnetized. Copper and lead, they will not form magnet. Okay, so iron will be easily magnetized, but magnetically hard will be steel. Okay, be more difficult. All right, so now we covered that. All right, so let's now go to 26. Which of the following can only be longitudinal waves? And longitudinal waves, again, are sound waves. They include sound waves. And so let's look at option A. It said can be reflected, refracted, and diffracted. That's all waves. And it said only B. Okay, that's the next thing right here. So only B. All waves can reflect, refract, and diffract. Transmit energy parallel to the direction of a wave oscillation, and this sounding good. Let's keep that in mind just a bit. Travels in a vacuum. Not all waves can do that. As a matter of fact, longitudinal waves cannot travel in vacuum, because longitudinal waves are sound waves, and sound cannot travel through vacuum. Travels at the speed of light. No, sound wave is not a part of the electromagnetic spectrum, so therefore it does not travel at the speed of light. And so B is indeed the correct answer. All right, let's jump to question number 27. It said diagram below shows a series circuit. And so here it said, what is the power supply? What is power supplied to the circuit when a current of 0.4 amperes flow through 10 ohms and the 20 ohms resistor? Now, first and foremost, now let's calculate this real quick. We have to calculate the total resistance in this circuit. And so the total resistance in this circuit, again, for a series circuit, resistor in a series is equal, which, matter of fact, let me say total resistor or resistance in a circuit is equal to R1 plus R2, okay, plus R3 and so on. Okay, let me say plus R2 plus R3 and so on. So that's the total resistance in a circuit, okay? All right, so let's now put our total right here. So our total is going to be 20 plus 10, which is 30. So let's say 20 plus 10, okay, plus 10 equals to 30. So 30 ohms will be our total resistance in the circuit. And so now let's calculate, now we're going to calculate our power. So what we want to find power now. So power, remember that power is equal to current times voltage. So power is equal to I times V, which is current times volt, times voltage. And so here now, just to make a quick note right here, right? Our current, which is our current right here, which is 0.4, okay? And we're going to calculate now to find in terms of resistor. All right, so we're going to find this now. We're going to find a resistance, right? Is 40 ohms. And so we're going to multiply this now, all right, by, so 0.04, so 0.4. We're going to multiply that by our 30, okay, and that will give us our 12. Okay, so that is 12. So that equals to 12 watts. Okay. All right, so let's look back at something here. One thing wrong here that I did. No, I cannot multiply by voltage. We do not have voltage. So I'm going to take out the voltage and give a different power formula right here. So this cannot work. So we're going to say that the power is equal to I squared times R. So let's put I squared times R for this one. Let me write that in. Instead, I'm going to have I squared here times R. Okay. Because there's not voltage, that's resistance. Times R. Okay, so that's going to be appropriate formula now. Right, and so once we have that, let me just take this back out here. Okay, let me just recalculate this. So I square, which is, so power now going to equal to I square, which is 0.4 square. So we're going to have 0.4 square, and 0.4 square will give us 0.16. So it's going to be 0.16. Then multiply that by R, and R is 30. And so 0.16 multiplied by 30, now we get 4.8. So 4.8 watt. All right, good. So this is the appropriate formula. All right, great. Now, if you have voltage and you have current, then you could use P is equal to I times V. All right. Okay, great. So our correct answer here will be option D. All right, great. Awesome. All right, so now let's go to our next question. And in our next question here now, it reads that the figure below shows a simple schematic diagram of a house circuit. Now, first and foremost, now let's walk through this, yeah? All right, so I want to notice something here with the circuit. So don't get too confused with diagrams and all that. You can actually point out what is the components are. So we have a switch right here. All right, we have going through here, these are fuses. So we have some fuse. We have switches again. Okay. And what I want to point out, I want you to notice where the switch is located, right? The switches, they are connected on the line that is X. Okay. That's what I want to point out right here. Switches, they're all connected to the line that is connected to X. So the switch right here that I'm pointing to right now will be the main switch, could turn off everything, right? So that could be like a breaker switch. Okay. So I'm going to point that out for you. All right, so the fuse are also connected. The fuse and the switches, they are connected to X. That's telling us something, right? Now, the other wire, which is Y, runs straight across and connected to these as well. Z, the broken line, and it goes to a special symbol right here. And you remember what that special symbol is? That's Earth. All right, I could just put that right here for you. This is Earth. All right, so we're going to see what they're asking us to do now. And so here now, the question said, what are the names of the letters Y, X, Y, and Z? And so X, again, let me just go back to it and show you right now. All the components in terms of the switches and the fuse, they are connected to X. Fuse and switches, they are connected to the live wire. So we know that X must be live. We also know that Z, for sure, is the Earth, because Z is connected to this symbol, which is the Earth, and so the other wire must be neutral. So we're going to say here going to be our live, neutral, and Earth. So live, neutral, and earth. Let's go down to the question. Live, neutral, and earth. So B is our correct answer right here in terms of what they represent. Okay, those are type of wires. All right, let's jump to the next question right here now. Question number 29. It reads that the figure below shows the magnetic field lines around two bar magnets in close proximity to each other. All right, or yeah, to each other. Okay, so the next thing here now that I want to look at on this magnet is the direction in which those field lines are going. Now, please remember that the field lines will leave the magnet at the north pole. So this will be north, so P will be north. R will also be north because it's going out. So it's going out. Okay. And Q going in, so this must be a south pole. So south is right here. S is also going in, so this is also south pole. So that's what I wanted to note and also know, that the field lines will leave the magnet at the north pole and enter at the south pole. So now we said name the poles, label P, Q, R, and S. So if you should go back to our diagram now, P and R must be the north, and Q and S, they must be the south. So let's now go to see where P and R are the north. P and R are north is only in this row. Yep. And then the two will be south, with this Q and S will be south. So B here is our correct answer. All right, great. Now let's go to the next question now. And in the next question now, we said that the series circuit shown below has a supply voltage of 9 volts. So we have 9 volts coming from the battery, and 3 resistors of resistance, 3 ohms, 5 ohms, and 10 ohms respectively. Again, remember that we need, when we're adding our total resistor or resistance within a series circuit, we just add them, R1 plus R2 plus R3. So therefore, the total resistance right here in the circuit, let's say R, so R will equal to 3 plus 5 plus 10. Okay, and so the total resistance here will be 15 plus 3 is 18. So this is 18 ohms. And the volt is 9 volts, right? It's a calculate the current flowing in the circuit. All right, and so good. Now we have our voltage, we have our resistor, and it asks us to calculate now our current. And so the formula we can use right here that contains voltage and resistor and current. So I want to look at this formula now, which is going to be V is equal to I times R, because we have voltage, we have current that we need to find, and we have our resistor. Okay, so this is the appropriate formula here. So to find current with this I, so I now is equal to V over R. Yep, V divided by R. All right, and so now we can put our voltage, which is 9. So 9 divided by 18. So you can say 9 divided by 18. Let's put that right here. 9 divided by 18, which gives us a half. So this is 0.5. Okay, 0.5. This is 0.5 amperes. So our correct answer here will be 0.5 amps. Okay, great. Let's go to the next question. Question number 31. It's a simple circuit is shown below. All right, we have component X, we have component Y. All right, and it said name the circuit components X and Y. All right, so let's point out a few things right here. X, this is a fuse. Okay, but you should know this is a fuse. All right, I'm sorry, that's a resistor, not a fuse. The line is not going through it. So this is a resistor. Let me just take that out. So this is a resistor. Probably I'm moving too fast. All right, so this is a resistor. No line is through it. So this is a resistor. All right, so let me just quickly label resistor. All right, I need to slow down a little bit. All right, so yes, so that's a resistor, and it is a fixed resistor because, again, it will be a specific value. Now, this is a diode here. This is a diode, but there's something specific with this diode. Notice the lines coming from the diode. That means this is a light emitting diode. It's giving off light, right? But if it was turned the other way, then it would be a light dependent diode, okay? So that's just point to note right there. The lines, arrows are coming away from the diode. So we're looking for a fixed resistor and a light emitting diode. And so option A, yes, is the correct answer. All right. All right, great. Now let's jump to the next question. Question number 32. I'm trying to really finish this really fast. All right, so a thermistor, okay, and when it's here about the word thermistor, what you're thinking about here is something that will apply some form of heat to function, okay? So again, if you think about thermistor, they are equipment that have a certain form of resistance, but they will change based on temperature, because the word thermo comes from heat, okay? All right, so thermistor. All right, so let's go to it now. It said that now, in which of the following devices is thermistor used? Okay, so they are used generally to detect temperature, heat, and so on. So they're generally for fire alarms. Okay, so if you have a fire, they will be triggered, and then you will get a response if it is in a circuit that connects it to a bell or alarm system. All right, so now 33 is the diagram now below shows a simple step-up transformer. So the fact that they give us here step-up transformer, that's a key thing right there. And so he said that you have a primary coil, you have the input voltage, you have the output voltage, and you have the core. Now he said given that the transformer is ideal, which row correctly shows its output voltage and current in relation to its input. Okay, so again, if this is a step-up transformer, then what must happen is that there must be an increase in the voltage. There must be an increase in the voltage, and there will be a decrease in the current. Okay, so the voltage will increase, but the current will what? Decrease. So here is option B. All right, so let's go to question now number 34. And question number 34, let's go through it quickly. All right, and so remember this diagram here, right? Which is the Fleming's left-hand rule, right? So we're going to remember the three fingers. So remember the three fingers. I'm going to use the three fingers now to identify what will happen in any given situation. The thumb, I'm going to start with the thumb. The thumb going to be very important, okay? All right, so let's go to the thumb. And so, 1 second there. Okay, the thumb. Okay, the thumb. Let's just 1 minute. Let's go up, right? All right, great. So what I want to notice about the thumb right here is that the thumb, again, let's think about the word thumb. So the thumb represents the force, okay, which is a thrust, okay, and the first finger represent the field. So remember that as a field. And the center finger or the middle finger represent the current. So center for current, okay? All right, great. Now, what does each of the label fingers shown above represent? And so again, the thumb is where we have the force, and a force will cause motion. And then the first finger is the field, and then the middle finger or the center finger is the current. And so this will be here our correct answer, D. All right, so question number 35. It said energy efficient LED lamps are increasing being used globally. It said calculate the cost of using a 0.015 kilowatt LED lamp for 8 hours daily. So this is the power. Let's just highlight what we have here. There's the power of the lamp. We use it only for 8 hours daily for 5 days. So 8 hours daily for 5 days. That's also important. The cost of 1 unit of electricity is $0.1. And so here asks us to calculate the cost of it. So let's just break this down real quick and fast. All right, so first thing we need to think about here is the total time of usage. And the total time of usage, we use it for 8 hours for 5 days. So 8 hours times 5, which is the 5 days, will give us a total of 40 hours, right? That's the time, 40 hours. Okay, just to make a note right there, 40 hours. And then now the unit of electricity here is 0.1. We need to bear it in mind as well. We have our power right here. So let's first calculate now our power reading. Okay. And so our power reading right here, what you can do is to multiply our time by the amount of money used right here, and then we're going to multiply that by our wattage. Okay, so let's go into it now. And so we'll calculate our hours. So we're going to say 0.015 multiplied by 40. And remember what this is? This is 1 unit of electricity. So therefore, this will be our kilowatt hours. So this now will equal to 0.015 multiplied by 40. That is 0.6. Okay, 0.6, right. And this is now kilowatt hours. Okay, that's kilowatt hours. And then we're going to multiply our kilowatt hours, which is 1 unit, by our cost. So we're going to multiply 0.6 multiplied by 0.1. And so here we will get here our 0.06. All right, and so therefore this is our cost in terms of dollars. All right, so this is our cost in terms of dollars. All right, so 0.06 is our answer here. All right, so this is option A. Option A is our correct answer. All right, great. All right, so now let's jump into the next part of next question. This is question number 36. It said a beam of fast-moving electron or electrons passing through an electric field between oppositely charged parallel plates. In which direction is the beam deflected? Remember now it is electrons. Electrons are negatively charged. So if electrons are negatively charged, it will deflect towards a positive plate. So it goes something like that. It will deflect towards the positive plate. Negative will attract the positive. All right, and so let's go to the question. What is happening here? Guys ask you which direction, and so they move towards the positive plate, and so this will be our correct answer for that question. Now let's go to question number 37. And for question number 37, it said Michelle uses a hair dryer of power rating 1,400 watt to dry her wet hair. Okay, and so it said the dryer operates using the main supply voltage of 120 volts. Which rating of fuse should be used? All right, so first I have a calculate current here to figure it out. And so here we have our power, which is, let's go back to the power rating up top here. Our power rating is 1,400. So I'm going to write it here, so I'm going to remember it. So it'll be 1,400. So power is 1,400 watts. And then now we have our voltage. So V here is equal to 120 volts. All right, so now we want to find current, because remember that the fuse is based up on the current that is flowing through the circuit. And so to find current, the formula we're going to use right here to find current is a formula that has power, current, and voltage. So going to be P is equal to I times V. Okay, and so current now will be here will be P over V. So let's say I is equal to P over V. Okay, and so here now in terms of the equation, let's plug everything in. So it'll be our power, which is 1,400 divided by 120, which is our volts, and this will give us divide 1,400 by 120. That is 11.67, right? And this is amperes. So this now is the current that is flowing through the air dryer itself. So which fuse is best to use here all right, is must be a fuse that is slightly higher than it, okay? Cannot be lower, because if a fuse is lower, the fuse will blow out easily, okay? So the best fuse to use right here is one that is slightly higher than the fuse that you calculate, or the current that you calculate. Because also remember that the purpose for the fuse is to break the circuit just in case the current is in excess. So slightly over is good, but when the current is way over, then the circuit will break. All right, now question number 38 here. So the diagram shows the temperature scale in degrees Celsius and also in Kelvin. It said, what temperature is 150 above absolute zero in degrees Celsius and also in Kelvin? First, let's point this out real quick. Absolute zero is 0 Kelvin, okay? Let's make a note of that. So 150 above zero, which is, say, something about right here, right? 150 is about here. So let's go straight across. We're going to see what we get here. All right, we can calculate this, as a matter of fact, rather than even reading the scale. So we could read the scale, or also we could calculate it as well. Now, firstly, if 150 above zero for Kelvin is 150, right? So we definitely know that Kelvin will be 150, because 150 above zero is 150, okay? Now, 150 above 273, right? 150 above 273, all you need to do is to minus 150 from 273. So on this side, we can simply say 273, because I saw that 0 right there. So 273. And I can use positive numbers and just convert back to negative number. Really don't matter. So we can say 273 minus 150. And so therefore we'll jump all the way up here to 123. Okay, so let's be 123. So we know that this is 123 right here. So we know that in degrees Celsius, it's going to be negative 123, just to make a note right there, because this is on the negative line. So it's going to be negative 123. Okay, so negative 123 and also positive 150 for in Kelvin. So we definitely know that A is our answer. All right. All right, so let's jump to the next question now. And we're almost there. All right, it said the figure below shows the simplified current diagram of an electric bell when the switch is closed. The circuit is complete and current flows. All right, so first now, let's see what they're asking us right here, motherfucker. Because current is flowing through the bell. Let's see if that is important. It said, which row in the table correctly shows suitable materials used to make the core of the electromagnet and the armature? So looking for the armature right here. So what is a suitable material that could make that? And also the core of the electromagnet, which is this. And so as you know that the core must be iron core, okay, for it to work, because it needs to be magnetized. And then the armature on this side also must also be a metal, okay? And so we're going to look for iron and iron in this case, okay? So iron and iron has two good materials there. So that's the correct answer there, B. All right, so now for question 40. All right, so which of these waves has the shortest wavelength? And so the shortest wavelength here will be the X-ray. And let me quickly just remind you in terms of the order from the largest wavelength to the smallest wavelength. And so the first one you have here is radio waves, and this one is the largest one. So I'm gonna start from largest to the shortest. And so radio waves, then microwaves, that's the next one here. Okay, and then moving from radio waves, all right? So radio waves, microwaves. After microwaves we'll go to infrared. Okay. All right, and from infrared, we'll go to visible light. Okay, and from visible light, we go into ultraviolet. Okay. And from ultraviolet, we go into X-ray. Okay. And then the last one will be gamma ray. But gamma ray is the shortest wavelength, but gamma ray is not here. So the one that is next in line there will be the X-ray. So this one is the shortest one. Okay. All right. So great. All right. So let's jump to question number 41. And question number 41 is that the graph below shows how the count rate of a certain radioactive isotope change with time as it decays. So how does it change with time as it decays? And so here now, let's just quickly go to it. We have our count rate on this side, and then we have our time on the X. And so here it said, what is the half-life of this radioactive isotope? The first thing to know is that half-life means the time taken for half the substance to decay, right? And so if we move from, say, 400, let's start with 400. Let's say we start with 400, right? The half of 400 go to 200, yes? So let's say start from 0. With this 400 is at 0. And 200 to go here, come all the way down. So there's 2. So from 0 to 2 is 2 hours, right? Let's use a different one to say if it will work out to be the same thing. All right, so let's use a different color, probably a blue. Let's say you start from, we could go from 300 to if you want and go to 150. So if we go from 300, all right, let's say go from 300, all right, and let's go to 150, where 150 will be here, okay, and so, no, 150 will be right here, okay, so notice all the time is moving. So to break down 300, matter of fact, let me break down 200. So 200 now break down to 100, right? Let's continue with the same pattern here. Start from 400 to 200. And then from 200 to 100, right? So 400 into 200 and 200 into 100. And if I go straight across with this blue line right here, take me to 4. So that's even perfect. All right. So here now is from the 400 to 200 is 2 hours. From 200 to 100, it is another 2 hours, which is 4. And if I go to 50, which is this, they should take us all the way across, and they should take us to another 2 hours, which is 6. Perfect. Okay, so the hours in terms of half-life will be 2 hours. So each half-life is 2 hours. All right, great. All right, so let's look at what our 2 hours is, and that is option B. Now 42. It said the half-life of radioactive cobalt is approximately 77 days. A sample contains 10 grams of cobalt 56. What will be the mass of cobalt 56 if the sample after 154 days? So in this sample after 154 days, what will be the mass of cobalt? Remember now we start with 10 grams, right? The half-life here is 77 days. Now let's work this out real quick. First and foremost, you think about the 10 decay into 5, right? So 10, let's think about the number of half-life. 10 decay into 5, and then 5 will decay into 2.5, and then 2.5 will be 1.25. All right, let's stop there for a little bit to see if we get to see what our numbers are first. All right, so let's think about it now, right? So our numbers here with the first half-life, okay? So our first half-life here, let's change this around. All right, so our first half-life here will be 77 days to break down from 10 to 5 grams. And then another 77 days to move from 5 to 2.5, right? And so moving from 5 to 2.5 had 77 to 77. All right, so let's say 77 right here. Okay, and the time it takes to reach here. So 77 plus 77 give us 154 days. Okay, so 154 days right here. All right, let me erase this. Okay, 154 days. 154 days. Okay. All right. And so if you have gone further, you go to 1.25 and so on, right? And so here we could stop at this point because it only takes 154 days to break it down to 2.5. So we have 2.5 grams of the substance remaining. So our answer there will be A for that one. Let's jump to the next question right here, which is question number 43. And we're almost out of here. All right, I'm really running against time. And so TH, all right, 223 decay into PA 234 as shown in the equation below. And so first and foremost, let's point this out. These are the mass numbers. by the way, right? These are the mass numbers. And so here now, it gives us the atomic number or the number of protons. And it said, what is the nature of X? And so there's no change in mass. Remember, the masses must be the same. There's no change in mass, so that would be 0 mass on that side. However, the mass number here was 92, but here is only 91. So therefore, what can we do with 91 to get 92? We're going to add 1 right here. Okay, and so therefore, the nature of X, if you notice, 0 mass, but with 1 atomic number, could be a beta particle. Okay, so beta is our answer. All right, so let's jump to the next part of the question now, right? So 44, it said, which of the following list the types of radiation in the correct order of increasing penetration or penetrative ability? And it is the same order which you name them, alpha, beta, gamma. So A, B, G, alpha, beta, gamma. So our correct answer here will be option C, alpha, beta, gamma in the same order. All right, let's go to question number 45. And in question number 45, it said that a polyethylene rod required a negative charge. It acquired a negative charge. It acquired a negative charge after rubbing it with dry cloth. How did the rod acquire this negative charge? So how the rod becomes negatively charged? For something to become negatively charged, it must gain electrons. If you lose the negative charge, then you become positively charged. So the rod acquired this negatively charge by gaining of electrons. So two things right here. The dry cloth will become positive because it will lose electrons. So the dry cloth lost electrons to the rod. So the rod becomes negatively charged. The dry cloth will become what? Positively charged. Just to make a note of that. So there's a loss of electron from the dry cloth. Right? There's a loss of electrons from the dry cloth, and the dry cloth will become positive. All right? All right, good. Now 46, it said, which of the following can convert sound energy into electrical energy? And it is a microphone that I'm actually using right now. And for 47, it said, which physical quantity is a scalar quantity? What is a scalar quantity? Scalar quantity only has size, no direction. Time, indeed, there is no direction. Weight is a form of force, so force acting in a particular direction. Momentum will act in a particular direction again, okay, because it deals with velocity, and velocity is this contain displacement, which is vector, acceleration, which is including velocity, which also is a vector quantity. So A is the correct answer. Number 48. Now we said the diagram below is a representation of the electromagnetic spectrum. And notice these again, which I gave the list earlier. You can even use this. This would be a good one to even go back to your question. Let's say you're in doubt, you could use it and go back to your question and say exactly one with the smallest wavelength. The one in the question was X-ray, as I remember. There was no gamma ray. So this will show that the wavelength here is shorter. Okay, so this is a good way to help you out a bit sometimes. All right, so sometimes these things do happen. All right, so 48 now, it said, which row in the table below correctly depicts electromagnetic waves that are commonly used for cooking? And so the diagram is not even helping us necessarily with this question, but we know that we use microwaves and we use infrared waves in cooking. Okay, so C will be your correct answer right there. Now for question 49, it said, when a magnet is moved through a solenoid, as shown in the diagram, voltage is induced. If the circuit is complete, current is also induced. It said, what change would not increase the size of the induced current? So again, once you put the magnet in the solenoid, current will flow and you get a reading on the ammeter. Option A states that I'm looking here for not increase it. What will not increase the current? Just to make a note there, not. Holding the magnet stationary in the solenoid. If you hold it stationary, nothing will happen. Matter of fact, by placing it in, while going in, you get a small reading. But if you hold it there, there'll be no reading after that. So therefore, A definitely will not increase it. So you can actually highlight A. But let's at B, increase the number of coils. Yes, more coils, you get a greater current. Moving the magnet faster in and out, yes, there's a greater current. And using a stronger magnet indeed give you a greater current. So A is indeed the correct answer. Last question, and we're out of here. I was really rushing this one. I'm really out of time. For question number 50, which of the following properties of a radioactive isotope makes it suitable for use as radioactive tracer in the human body? And so a tracer must be short-lived. That's the first thing. A tracer must be short-lived. So the 2 years, we're going to take these out, right? Because if it's living too long in the body, it's not good. It is not good. You'll have problems with that, or a higher possibility of getting cancer. The 12 hour is good, but let's now decide between alpha and beta, which is the best one to use here. The first thing with alpha, alpha is easy to ionize, so it is one that is easily ionized, and so therefore it could cause some reaction in the body easily, right? Because it forms ions really quickly. And so beta will be our best option right here. Okay, so beta will be our option for this question. Again, this is a rush one. Sorry for rushing. I really pressing for time. Again, keep safe. Good luck on the examination. I will be doing another review for physics as well, so look out for those. All right, or at least one more. All right, so keep safe. Good luck on the examinations.